So hi guys, welcome to the lecture number 3 for the rocket propulsion, and today we are going to see the next chapter, that is the rocket performance. So in this chapter we will build the basics as well as the equations regarding the rocket. And as you know, my name is Ujjwal Srivastava and I am doing my master from IIT Kanpur, and here I have given my number. So if you want to contact me for the personal guidance or any help from my side, please contact me on this number. You can WhatsApp me, you can call me anytime. So let's start the class. And one request guys, whoever is coming for the videos and watching the videos and watching lectures, so please subscribe and share with your friends. So it will help to both of us, right? So please subscribe the channel at least. So let's continue. Let's build our basics first for this performance. So there are some topics which is related to the gas dynamics which will come here. So first I will tell you all those concepts, then after I will start the main concept. So first you write stagnation properties. Okay, right. First you write stagnation properties. Let me define now what is called as stagnation. So write stagnation property is defined as when a flow, or you can say the fluid flow, of course, when a fluid flow brought at rest means the velocity is 0, at rest by isentropic process, is called stagnation point. Here you can erase this and you can call it stagnation point, not property. Fine. That means when a fluid is going to at rest at that particular point, so that particular point is called as a stagnation point, and stagnation point we denote it as a naught. That means any property, the property is P or subscript naught, we use as a stagnation. Stagnation property. So now this is basically property. P is nothing but your property, but after some time we'll see this. The P naught is of course the pressure. So this is called as a stagnation property. So these things we'll study in the gas dynamics when we'll study the gas dynamics in very depth, and we'll derive all the formulas for stagnation point or stagnation properties. So please, whatever I am writing now, please remember this formula, and we'll derive this by the law of thermodynamics as well as the gas dynamics. So first you write 3 formulas which you have to remember. So write T naught divided by T is equal to 1 plus gamma minus 1 divided by 2 m square. Okay, then after P naught divided by P is equal to T naught divided by T. You can put this T naught divided by T value, this value over here. So only I am writing T naught by T to the power gamma by gamma minus 1, gamma minus 1. Then third one is the rho naught by rho is equal to T naught by T to the power 1 by gamma minus 1. So please remember this formula, all these 3 formula, This is very important actually. I'm not giving any numbering for this, right? Let me define what are the things over here. So here T naught, nothing but your stagnation temperature. Stagnation temperature. This stagnation is also called as the total. So you can call it the total temperature or stagnation temperature. Fine. This T is nothing but your static temperature. Static temperature. Fine. This P naught, nothing but your stagnation pressure. This P is nothing but your static pressure. Similarly, rho naught is nothing but your stagnation, or you can say the total density, and rho is nothing but your static density. In this formula, two things are also there. This m is nothing but your Mach number. This Mach number, see, always remember, this Mach number is corresponding to this temperature, right? So when we solve the problems, so we'll understand what does it mean, corresponding means. Again, the gamma is given as a specific heat ratio. It is nothing but your Cp by Cv. Cp means specific heat at constant pressure, and Cv means specific heat at constant volume. All these things we'll study in thermodynamics, so don't worry as of now. This Mach number is nothing but the velocity of a fluid flow divided by the speed of sound. So write definition for Mach number, although we'll study this, but still we write. It is a ratio of velocity, or you can say the local velocity. Local means the surrounding velocity. Local velocity of fluid to the speed of sound. Fine. So now this Mach number is basically, if write some basics for this, if Mach number is less than 1, that is called a subsonic. I think you know all these basics, because if you are preparing for the GATE exam, so you must know all these basics from your college. But still, I will tell all these things in a respective subjects for the gas dynamics or flight mechanics, all these things, right? If Mach number equal to 1, that is called the subsonic sonic condition, or you can say the subsonic condition is a sonic condition. If Mach number greater than 1, so we'll have the supersonic. In between there is something called transonic or highly compressible. All these things we'll study all these things in a gas dynamics. Supersonic condition. Fine. Now you understand. Okay. Now you write. Now you write critical state. Okay, right. Critical state properties. Right. At Mach number equal to 1, that is your sonic condition. That means the sonic condition. the properties will reach a state called as critical state. That means, see, suppose when Mach number is less than 1, okay, so let's suppose less than 1 means 0.3, let's suppose. So it will increase, and after some time, or after a point, or after a while, it will goes to 0.9, then after 1. So it is approaching the 1 value. So when the Mach number is equal to 1, that is called as the critical state. That means the Mach number equal to 1 means sonic condition, right? So all the static properties will be converted into critical properties. So please don't confuse with the critical Mach number. See, let me again told you. Fine. So okay, I'm writing it here so that you can understand. If Mach, okay, it is already written fine basically. See, if the Mach number, say over here, if Mach number is equal to 1, that condition is called as the sonic condition, as I told over here. Fine. Now, so when the Mach number is equal to 1, then all the static properties, static means this one, this rho, this p, this t, will become the critical property. Critical means t star. So this t becomes, for this t becomes is equal to t star, this p becomes p star, and this rho becomes rho star at Mach number equal to 1. But it doesn't mean that if the Mach number equal to 1, it doesn't mean that it is a characteristic, or you can say the critical Mach number. No, critical Mach number is something called different. So we will study in the gas dynamics. It is a Mach number at a sonic condition basically. So all these conditions at this Mach number equal to 1, the static properties will be the critical properties or nothing else. Fine. Now, so these three. Then after, the velocity become v star. Okay. So all these things we will reach at the Mach number equal to 1. Now you write. Now you write the formula. That means whatever I have written here, this t, p, and rho. We will replace this t as a t star at Mach number equal to 1. So if you keep Mach number equal to 1 over here, so this t becomes a t star. So let me write. So t naught divided by t star. T star means at Mach number equal to 1. That is equal to 1 plus gamma minus 1 divided by 2 into 1 basically. So Mach into 1 means Mach number equal to 1. This one. So we will get the 1 plus gamma divided by 2. Fine. Again, if you put the p naught divided by p star, so you will get 1 plus gamma divided by 2 to the whole power gamma by gamma minus 1. Fine. Similarly, if you put rho naught by rho star, that means 1 plus gamma divided by 2 power 1 by gamma minus 1. So what it mean? This all the things is happening at Mach number equal to 1, at m equal to 1. If you put m equal to 1 in the above equation, here, so you will get the same value as this, 1 plus gamma by 2 or something. Fine. So all these are the from the gas dynamics. We will study in depth when we will study this. So as of now, please remember this types of formula. Now next, mass flow rate through a duct. So now understand what is mass flow rate basically. Now understand what is the mass flow rate. Let's suppose you are having a duct. Draw like this. Fine. This is the exit of the nozzle. See. Now right. This is the storage chamber. Or sometimes called is a rigid. Basically it is a rigid. Rigid means, what I mean, rigid means the volume is constant, the volume is not going to change because of rigid. So the velocity is 0 over here in this storage chamber. If the velocity is 0, then I told you in this, if the velocity is 0, that is called as a stagnation point. Stagnation point means P becomes P naught, T becomes T naught, and all these things. So P becomes P naught, fine. T becomes T naught in this, right? This is called exit of nozzle. So basically, in the rocket propulsion, or you can say the rocket engine, mostly you use the CT nozzle. From here to here, there is a conversion part. And from here to here, it is a divergent part. And in between, somewhere here, in between, somewhere here, there is something called throat. Throat means nothing but your minimum area. Fine. Now you understand. So here the pressure will be the PE, area will be the AE, and the temperature will be the TE. Fine. So basically this point is known as the throat, or you can say the minimum area. So now understand, when Mach number is equal to 1 over here, that means here, Mach number equal to 1 over here, that means at throat, you can say the at throat, then A minimum, that means this minimum area is equal to A star, or you call as a throat, becomes A throat, right? This throat is nothing but written as a, see, this throat is nothing but written as a throat. Okay, this minimum area is written as a minimum. So if the Mach number is equal to 1 at this point, at this location, at this throat, then that is called as the A star. And this A star is nothing but your called the choked area. I will tell you what is choked and all these things when you study the gas dynamics. So this is called as choked area. Fine. So now, so again we'll derive this, draw this figure in the gas dynamics, and we'll derive the formula which I am going to write. So m dot, that is the mass flow rate through the duct, divided by the area into T naught, that is your chamber pressure, divided by the P naught into R divided by gamma. R divided by the gamma, fine, is equal to root under 2 by gamma minus 1 of P by P naught 2 by gamma minus P by P naught gamma plus 1 by gamma plus 1 divided by gamma. So this as a basically your mass flow rate. So see how much is mass is getting flowed from this throat, that is calculated by this formula. So A is given as this one, A throat, fine. T naught is given as this one, this, okay. P naught is also given over here. R is basically your characteristic as constant. Gamma is also given. All these things will be given to you. They can ask you mass flow rate, fine. The same thing we can find from the another way, or you can find the mass flow rate by another equation, that is called the mass flow rate equal to rho A V, fine. If the rho is given, area is given, and V is given, then you can find the mass flow rate from here. Now you write the maximum mass flow rate. So what I mean by maximum, we'll study after some time. So how much flow is getting, how much flow is going from this small area, that maximum flow, that is called the maximum mass flow rate. So first you write the formula, then after we'll study what is this. Okay, now write. So maximum, m maximum divided by, so m, when maximum mass flow rate will happen, when the Mach number becomes equal to 1 and the minimum area becomes A star. That means when the Mach number becomes equal to 1, that is the area, that means area becomes a A star, that is a choked area. So at that particular point or that particular location, we will get the maximum mass flow rate. So right, maximum mass flow rate is the area A star into T naught by P naught into R by gamma is equal to 2 by 1 plus gamma plus 1 divided by 2 gamma minus 1, fine. This is also a equation for the maximum mass flow rate. This equation will derive in the gas dynamics very neatly and very clearly. Till now we are doing only gas dynamics, basics of gas dynamics, which is basically going to use in this rocket propulsion chapter. Now you write the rocket performance. Now let's start the rocket propulsion. So let me once again summarize what I have studied till now. See, first we have seen the stagnation properties. So what is the first called as the stagnation point? That means when any fluid flow brought to at rest by isentropic process, then called the stagnation process. So what does it mean by isentropic? Let me define you. Isentropic means reversible plus adiabatic. You might have known this from the thermodynamics. Now, then after I have written the formula. This formula we have derived from the gas dynamics and thermodynamics. We will derive once again and we will study the gas dynamics. Till now, remember this formula. This T naught is nothing but your total pressure. T is nothing but your static pressure. This gamma is nothing but specific heat capacity. Specific heat ratio, and the m is nothing but your Mach number. Fine. Mach number defined as the velocity divided by the area. I write in the difference over here. If Mach number less than 1, that is called as subsonic. Equal to 1, sonic condition, supersonic condition. So in a gas, in gas dynamics or rocket propulsion, mostly supersonic occurs. because the rocket is going to fly at higher Mach number, that is a less than greater than 2, greater than 3, or equal to 4, equal to 5, like this. So always we will have the supersonic flow. Mostly supersonic flow will be occur. Then again we studied the critical state. Critical state means when the Mach number reaches to 1, that means at particular location all the properties, pressure, temperature, density, becomes the star property. So T becomes a star, P equal to P star, and rho equal to rho star. Basically it is a convention, you have to follow it at Mach number equal to 1. This is not a characteristic equation basically. Fine, at Mach number equal to 1. Then again I have kept the Mach number equal to 1 over here. Then you got the this value T naught by T star at Mach number equal to 1, and this is much. Fine. Then after I told you mass flow rate through the duct. This is a duct basically. So how much mass is getting flow from this duct is written in this formula. This formula will drive in the gas dynamics very neatly and very clearly when you study this. Once again, how much that means maximum mass flow rate at what condition that will be occur. So that will be occur at Mach number equal to 1. Then the throat becomes a star, that means a choked area. So at that time we'll have the maximum mass flow rate. How? Let's understand. Now you write, let's start the rocket performance. Write the rocket performance. Right. Consider a rocket system shown below. That means in rocket majorly the payload is also there. Mostly the nozzle and combustion chamber is there mostly, basically which works mostly. So in figure below, now we draw a very neat figure of this. Draw this. Now you write, draw this very neatly. First you write over here, this is the chamber pressure. PC and PT are both the same thing. Chamber pressure, chamber temperature. This is basically your combustion chamber. I'm talking about the rocket. So this is a combustion chamber. Okay, fine. Combustion chamber, right? Now there is one throat over here, that means the combustion nozzle. Then after you'll have the Dewey nozzle. Fine. At this point this is called a exit of CD nozzle. So in rocket most of the time we use the CD nozzle. Most of the time is nothing but basically always, you can say that always we use the CD nozzle. The reason is we will study in the gas dynamics, because why use the CD nozzle, we will study in the gas dynamics. So as of now please write this. Now you can this is basically your A throat, right, as your A minimum, or obviously it will be choked because of the CD nozzle, because you need the supersonic value, so it is also equal to the P star. So now if you see this rocket like this, So we will have a rocket like this. So this is your basically this is your exit of the rocket, and after this we'll have a some rocket and all this thing. Basically this is your rocket basically. So we are talking about the combustion chamber and the nozzle part. Fine, let's go. So here we are having the PE, that is the exit plane pressure, the AE exit area, and the TE. So let me write all this in. Basically this is your combustion chamber. So write here PC is nothing but your chamber pressure. Here PC is a chamber pressure. It is similar to this one. Here it was P naught, that is a storage chamber, so it is similar to the PC. It is a chamber pressure. Similarly, TC is nothing but your chamber temperature. This A star is nothing but your throat area, I mean the choked area you can say, or throat area also you can say, choked area. This P is nothing but your exit plane pressure. Fine. This TE is nothing but your exit plane temperature. You can say the temperature basically. Nothing is called plane. Okay, we can say exit temperature. This AE is nothing but your exit area of nozzle. So now write. Now write some wordings. You write some wordings. The maximum required to get, requirement you can say, the maximum requirement to get the supersonic flow at the exit plane is the throat must be choked. That is mass flow rate through the nozzle should be maximum. Fine, let's understand what happens. So let me take this diagram once again, then after we just so now you understand what happens basically. Now understand this. First, in this combustion chamber, this is a combustion chamber basically, we have the fuel plus oxidizer. So it will combust. That means the fire will be there. Understand this point basically. Fire will be there. So if there is a fire, that means the heat is getting generated. So heat is getting generated. First let me explain, then after I will write. So heat is getting generated, and this is the due to the heat generation we are having the temperature increment as well as the pressure increment, right? So this chamber pressure is much greater than this PE, from here PE, right? So now if the pressure difference is there, that means the flow will be a start. With this we'll study this in a gas dynamics basically, because at higher, see, one point is here and another point is here. This is your higher pressure and this is your lower pressure. So the flow will always flow from higher to the lower. This is your basic nature of the thermodynamics, or you can say the basic nature. This is basically the second law of thermodynamics, and you can say the basic nature of everything. So everything is flowing from the higher to the lower. So this PC is higher, much higher than the PE. So the flow will start to accelerate from this nozzle. Now you understand, in this combined nozzle, the flow will accelerate because the area is getting decreased, right? So by the Bernoulli equation, till now there is no any supersonics, it is a subsonic. So we can apply the Bernoulli equation. So by the Bernoulli equation, if the area is decreasing, the velocity must increase, and the velocity is increasing, then pressure must decrease, right? In this, pressure will be decrease. When the, now you see, when the flow will reach at this point, this throat point, then this velocity, see, velocity is increasing and it is approaching to Mach number 1. That means it is approaching to the speed of sound. So when at this point this velocity reaches at a value, that means when this velocity is reached at Mach number equal to 1, that means this velocity becomes equal to A. That means this velocity, that means the flow velocity or fluid velocity becomes the speed of sound, that is the Mach number equal to 1. That time, now understand what happens. So from this nozzle area, the flow is get choked. The fluid flow gets choked. Choked means lock. Lock means, choke means lock. Lock means what happens? You cannot increase the velocity after this velocity, which is already reached at Mach number equal to 1, or at a speed of sound. Fine. So that time there will be mass flow from here, right? That is also fixed. Mass flow is also fixed. So that at that particular time or at that particular location, the mass is fixed. Thus that mass is nothing but your maximum mass flow rate through this nozzle at choked condition. So that's what I have written over here, maximum mass flow rate at the choked condition. So it is always happened when the nozzle is choked. That means throat must be choked. That is, the nozzle is choked. Fine. Now you write whatever I have said here in wordings. Now you write. Sorry. Now you write. First, now you write note. In note we'll write this whatever I have said. See, in the combustion chamber, the fuel in oxidizer, I can also leave this part, because if I told you to remember the mass flow rate is maximum at the choke condition, but there is no meaning of this. You understand the physics behind this, behind the every topic or every concept. Why it is maximum, what happens when it happens. So all these things you have to understand. That is why I'm I'm writing this, the concept behind this in a note. So please study it like this. In the combustion chamber, the fluid and oxidizer, the fuel and oxidizer react and start the combustion. Due to combustion, the heat transfer, the heat is getting generated. Due to this heat, the pressure and temperature start to increase. That is your PC and TC. Fine. One point. Another point. Now understand. Then now due to pressure difference between combustion chamber and the outer you can say the exit area, or you can say the at exit, CC and exit, the flow start to accelerate in the converging part of nozzle. Fine. When the velocity accelerate means velocity is increased, obviously. When the velocity reaches at Mach number equal to 1, that is basically velocity is equal to speed of sound, then flow is choked. That means the flow is locked, which means that if you further increase the flow is choked. That means we can write it's choked, it's locked. So the velocity will not increase after this value. Now I'm writing one word over here, even after reduced the exit pressure So why I'm writing this word over here, even after reduce the exit pressure. So see, in this figure it was a PC, right, and it was a PE. So let's suppose the PC minus PE is something as a 10. Let's suppose the difference is 10, If you decrease this P value, so the difference will be higher. Difference will be higher, of course. That means the PC will be higher. See, actually, if you decrease this P value, that means the PC will be positive, and the difference of this will be higher, right? If you decrease this, the difference of these two pressure will be higher. That means the flow will accelerate again faster than the previous one, but it is not possible after a certain value of velocity or certain Mach number equal to 1. You cannot increase the velocity even after reduce the exit back pressure. You can say the exit pressure. That's what the main concept over here. Then so now right after, so due to this mass flow rate is fixed. Mass flow rate is fixed, and this fixed mass flow rate is basically maximum mass flow rate, because if you cannot increase the velocity, so mass flow rate is a fixed. We cannot increase the mass flow rate, so that fixed mass flow rate is basically maximum mass flow rate. Basically maximum mass flow rate. This is the main funda of here, right? These things I have written extra for you only, because you can understand why this is maximum and why and when it is maximum and what is maximum basically. So these things I have written for you only. So please you can say please revise this, so you can get the very good knowledge of this, because in interview they can ask you why it is maximum, how it is maximum, and all those things, right? So now you write. So okay, so from here I'm going again. So as we know, at A throat, that is A star, that is the A minimum, we have m dot maximum, fine, at Mach number equal to 1 basically, equal to 1. Now right, we know this, the mass flow rate, maximum mass flow rate formula, this one, right? So let me copy this. You know this formula, right? Now you understand. What I'm doing is, I'm doing m maximum is equal to root gamma into this value. This value, right? Okay. Root gamma into this value, fine, in one bracket, and this P naught, I mean the PC, you can write the PC over here, because you are talking about the chamber pressure. So this is basically PC, TC and PC, right? So this PC into A star. Fine. Eighth root or A star basically. Divide by root under RTC. Hope you have got this. So now understand this term I am taking as a f of gamma. Right? So right, mass flow rate, that is the maximum mass flow rate, is equal to PC into A star divided by the root under RTC into f of gamma. This is basically f of gamma. So let me write it clearly. F of gamma. So this is equation number first. So in rocket propulsion, what is the, or you can say the, in any you can say maximum mass flow rate through a duct. So you can use this formula. Fine. Here f of gamma is nothing but your root gamma. You have to remember also this 2 divided by 1 plus gamma divided by 2, gamma plus 1 plus gamma divided by 2 into gamma minus 1. Fine. This is your equation 2. Fine. Now let me take one you can say one extra term that is called as the characteristic velocity. It is denoted as a C star. So the C star is nothing but your root under RTC divided by f of gamma. So if you keep this in this equation number 1, so you will get maximum mass flow rate is equal to, or you can say the equation number 3 for this one, because sometimes they also say find the characteristic Mach number. So we'll suppose this is equation number 3. So mass flow rate becomes PC A star divided by C star. Fine. So mass flow rate we have calculated in terms of, so mass flow rate we have calculated in terms of chamber pressure, throat area, okay, TC, that means the chamber temperature, R, and the f of gamma first. Then after we have calculated in terms of the also the you can say the characteristic velocity. So this characteristic velocity is a function, basically these are the function of temperature, chamber temperature, of course, this one R, okay, gamma, okay, and the last one is the M, it is a Mach number, not Mach number, it is a molecular, exactly. This M is nothing but your molecular weight. It's not Mach number, it's a molecular weight. Fine, this is a function of this one. How you can please because the R is nothing but your R divided by M. So this is a function of R and M. Now you understand. Okay. So now you write. So the first equation for the rocket is given by F is equal to m dot VA plus AE P minus PA. let it be equation number 5. Now you write. Okay, till now please you revise till now, then after we'll continue in next class, because it's a very hectic to understand all this concept of from gas dynamics. So please revise till now, then after we'll continue. So as of now we have studied the basics of rocket performance. So please guys revise till now, and we'll finish the GATE syllabus before our exam, that is before January of course. We'll finish this in December last or January first week. We'll finish all the syllabus. Then after we'll start the test series for different subjects. So if you need any guidance from my side, any personal guidance, please contact me on this number. And whoever is coming to watch these videos and watching this lecture, please subscribe my channel and share with your friends. It will help me to you can say teach more and more to you in the free of cost. So please study till here, then after we'll continue in the next class. Thank you so much for being patient with me, and please revise till here and try to see the previous year questions, so that you can understand what is the level of questions of any you can say subjects. So till now we have finished the space dynamics. So please go and solve the previous year. Although I have also solved the previous year all the questions in our GATE syllabus or in our channel. So please go and watch if you are unable to solve, but please solve by your own first, then after see the solution. Thank you so much. Have a good day.